What shape have I drawn on the board? A circle, okay? Now, you should know a few formulas to do with circles, right?
1/2 pi r?
Not quite. So you should know a formula for area, and you should know a couple of formulas for circumference. Okay. Yeah, circumference is 2 pi r, or what's 2 radii put together? What does that make?
1/8.
A diameter, doesn't it? If you put 2 radii back to back.
Yeah.
So you could also say that that is pi d. You could also say that's pi d. Okay. Area? Yeah, good. Pi r squared. What would it be in terms of diameter?
It's diameter times diameter, so we can just say.
Well, hang on a minute.
It's a radius. It's a radius.
So what would a radius be equal to in terms of a diameter?
1/2.
Times the diameter, yeah. Half a diameter, okay? So if we stick that into this formula, we get pi times my radius squared, which I'm saying is diameter over 2, squared. Good, so it become pi d squared over 4, okay? That's like an Alex special. That's an extra one there for you, okay? So you can also have pi d squared over 4 if you want to. Okay, good. So these are the formulas which are related to circles, okay? So obviously if you have a radius here, then these are the 4 formulas, circumference and area related to circles. Now what this question is getting at is saying, well, what if you don't want to look at the entire circle? What if you only want to look at a bit of a circle? Now there's 2 ways that you can look at bits of circles. The first way is just simply by taking a chunk of that circle. So you literally get something that looks like this, okay? So let's say, for example, that angle there is 30 degrees, for example, okay, in some radius. In fact, let's just do this generally. Let's not say 30 degrees. Let's just say it's any old angle we like. Let's just call it theta. Okay? So you've got a radius and you've got an angle between those 2 radii as well. What would we call that bit of the circle? It begins with an S.
Sector.
It's a sector. Good. So a sector is just a chunk of the circle, slice of the circle. Okay? What would a segment be?
Like when you put a chord.
Absolutely right. Yeah, exactly. So basically, if you take a circle, so I'm just going to take a sector in this case and just generalize it from there. And yeah, if I put a chord, remember a chord is a line which joins one point on the circumference of a circle to another, okay? Then the segment would be this piece in here. Exactly. Okay. Good, well done. So you've got sectors and you've got segments. But I think we can take the circumference and area formulas and convert them into sectors, and we can use that to find segments. Okay? So think about it. How many degrees are there in a full turn of the circle?
360.
There's 360. So if I get rid of that, okay, and I went all the way around, that would be 360 degrees. Okay? But here, with this sector, I'm only looking at a chunk of that 360 degrees. I'm only looking at theta lots of that 360 degrees. Exactly. So I should just be able to convert the circumference and area formulas for the sectors just by thinking of it as a percentage out of 360. It's just going to be theta out of 360ths of the circle. Okay? So now this wouldn't be circumference anymore. What would we call it? Arc length? Would that make sense? Yeah? It's a bit of the circumference. Okay? So arc length would just be theta out of 360ths, okay? Exactly. All times by pi d, depending on which formula you want to use, okay? So that bit is just the circumference. But all the idea of this is that we're not looking at the entire circumference anymore, we're only looking at a bit of it. We're looking at theta out of 360. So for example, if theta was 90, for example, it would be 90 360ths, which would be a quarter of the circle. Or if theta was 30, it would be 30 360ths, which is 1/12 of the circle. Yeah? So it's just theta out of 360ths. What would the area of that sector be? Yeah, exactly. It's the same kind of idea. It's theta out of 360ths multiplied by whatever area you want to use. I vote pi r squared. Okay, that there is exactly the same as the area of the circle. Okay? So that's the idea. That's what's getting at this question. So my question is, how could we generalize it to find the segment? Okay? Now, we will meet it. We haven't met it yet. But the idea is, can you see here that there is a triangle going on? So there's my theta. There's the angle in my triangle. And that's a radius, and that's a radius. There's two side lengths. So what I literally have here is a triangle that looks like this.
Equilateral?
It's not equilateral because we don't know whether that is R. Okay? So the way which we work out the area of a triangle like this, and we will prove it to you, I'm not going to prove it today, but does anybody know it?
Yeah, since it's an isosceles, we just like first of all, the area of the triangle is 1/2 base times height.
Mm-hmm.
We don't have either, so we're just going to use the sectors.
So what we can do here is we can think about it like this. I'm just going to draw it slightly differently just for the sake of clarity. So I'm just going to rotate it like that. So that's my theta, that's R, and that's R. What I'm going to do is I'm going to say, well, I know that my area of a triangle should be half times the base times by the perpendicular height. So I'm after the perpendicular height. Okay, well, if I think about this, this is just going to be a right angle triangle. This is just going to be a right angle triangle, isn't it? So the right angle triangle, I want H in terms of theta and R. Okay, that's the opposite. That's the hypotenuse. So I'm going to say H should be equal to R times by the sine of theta. Does that make sense? Yeah? So in other words, if I put my R back in now, okay, the area of my triangle should be half times by my base, which is R, times by my height, which is R sine theta. Does that make sense? Or if I do this more generally, it's going to be half R squared sine theta. Okay? So in other words, to find my segment, would you be happy that I'd use my entire area, which is the area of my sector? That's just going to be this thing. Yeah, exactly. So it's going to be theta 3/60ths times by pi r squared, okay, minus the area of my triangle, which I've just shown to you is a half r squared sine theta. Okay? So that's how to work out the area of that particular segment there. It's basically the whole area, take away the bit which I don't want, and I'll be left with the bit which I do want.